My left hand, which was in the hot water, feels cold, and the one that was in the cold water feels cold now. So I guess from this we can conclude that our fingers tells us about temperature relative to its own temperature.
Yes. Good morning, Betty and Malit.
Good morning. Okay, so is everyone ready for today's experiment? It's going to be about heat and temperature.
Yes, the concepts of heat and temperature are quite important to our scientific understanding of nature. Water boils when heat is supplied to it and when the temperature reaches a certain boiling point. So now we can discuss about the two concepts, temperature and heat.
Yes, and the first question is, what is heat? Well, heat is a form of energy and it refers to the kinetic energy of molecules in a system. And when we use this as the question, how much heat, we are actually referring to the kinetic energy of molecules in that system. So mass is a very important factor when we are trying to calculate heat. And we also have to remember that heat is not a substance or a matter, and it does not flow between molecules just like water flowing in a river.
If it's not something that flows, then why do scientists often speak of heat flow or heat transfer?
Well, that's a very good point. When scientists speak of heat flow, they're saying that a substance is either gaining or losing kinetic energy. You have to remember that a molecule or a substance does not have heat, but it has kinetic energy when it's moving or vibrating.
So here it is important to realize that heat is associated with the kinetic energy of molecules in a substance. So now what is temperature and how is it different from heat?
Well, temperature is the average kinetic energy of molecules in a system, and it lets us compare the kinetic energy of molecules in one system to the kinetic energy of the molecules in the other system. For example, if I touch a stove and if I say that it's hot, what I'm saying is the average kinetic energy of the molecules in the stove is greater than the kinetic energy of the molecules of my finger.
Okay, so I think there is a really good representation for the point you just raised. Our fingers explain temperature in terms of their own temperature. For example, here we have some hot water and cold water and lukewarm water. So now I'm going to put my left hand in the hot water. Okay. And let me move this. Okay. So here I'm going to put my left hand in the hot water and my right hand in the cold water. Okay. And now I'm going to put my hands in the lukewarm water. What do you think my hands feel?
I think both hands will feel the same temperature because they are inserted in the same beaker.
I don't think so. I think they feel different. The one you put in the hot water will feel colder, and the one you put in the cold water will feel hotter when you put it in the lukewarm water.
Yes, I still don't understand this. Maybe I should try it myself.
Yeah.
Oh, you're right. My left hand, which was in the hot water, feels cold, and the one that was in the cold water feels cold now. So I guess from this we can conclude that our fingers tells us about temperature relative to its own temperature.
Yes, and we can see that our sense of touch is not an accurate method of measuring temperature. Instead, we have to use thermometers to realize the exact temperature of a substance.
Can you tell us the difference between temperature and heat?
Yes. Temperature is not energy and temperature is not heat, but temperature is the average kinetic energy of the molecules in that substance. So the temperature gives us information about the motion of particles in that substance. But here it is important to note that it does not tell us any information about the number of molecules in that substance. And it is also quite obvious that hot that the terms hot and cold refer to the temperature and not the amount of heat that the substance contains. And the molecules in a substance do not get hotter or colder, but they just gain or lose kinetic energy.
Okay, so now we're clear on the concepts of heat and temperature, and our next experiment is going to be about the two effects of heating. So, let me break this. But before going to that, I think we need to talk about the two effects of heating. And when we heat a substance, we raise its temperature. But this does not mean if you keep on supplying heat, the temperature will not increase indefinitely. At the melting and the boiling point, the temperature will stop.
Yes, so even if you continue heating a substance at the boiling or melting point, we can no longer see any increase in the temperature.
Yes. But we agreed that heat is a form of energy. Then whether the heat supplied or after the melting or boiling point, I mean, if there's no increase in internal kinetic energy, then where does the heat go?
Okay, so that's a very good question. The energy or the heat supplied in this case is used to convert the state of a substance from one state into the other state. And we refer to this heat as latent heat, which means hidden heat. And we refer the term latent heat because the heat that's applied in the process is not changing the temperature of the system. It's not raising the temperature. And we can demonstrate this experimentally by boiling water. So, why don't you place the beaker on the boiler so that you get boilers? Let's see. What's the temperature?
20 degrees centigrade.
Okay. So now we start boiling the water, and we have a stopwatch here, and we'll be recording the temperature every 30 seconds. Okay, so let's start this.
Mm. 30 seconds.
What's the temperature?
29 degrees centigrade.
29. Nice. Okay.
Minutes.
64.
Six minutes.
88. No, it's 88.5.
6 minutes and 30 seconds.
88.5.
Seven minutes and 30 seconds.
88.5. Okay, that's enough. Thank you so much, Preeti.
So our experiment turned out as expected, and so let's analyze the results of our experiment. Okay, so as you can see over here, the temperature was increasing at first for the first 6 minutes. First it was 19 and then 29, and it was constantly increasing. However, when the temperature reached 88.5, it did not increase. It became 88.5 for the next 1.5 minutes. So from this we can understand that when we supply heat, the temperature increases at first, but once it reaches its boiling point, the temperature will not increase. And we can also demonstrate this data graphically. And as you can see over here, at first the graph is a straight line, which means as we supply heat, the temperature is increasing constantly. But as we can see over here, a horizontal line starts to form, and if we keep on heating the substance, the temperature will still be at 88.5. So from this we can conclude that the temperature will not increase at its boiling point. Okay. But something is troubling me about our results. We have learned that water boils at 100 degrees centigrade. However, we got that the boiling point of water is 88.5. So does this mean that our thermometer is not working correctly?
No. You know that water boils at 100 degrees centigrade only at sea level, right?
Okay.
So we can take Addis Ababa as an example, and Addis Ababa is about 2,000 meters above sea level, and the atmospheric pressure is less than the atmospheric pressure at sea level. And therefore the water boils at a lower temperature.
So our thermometer is working correct?
Yes.
Yes, but if we expect a boiling point less than 100 degrees centigrade at an atmospheric pressure less than that of sea level, then can we expect a bigger boiling point than 100 degrees centigrade when the atmospheric pressure is greater than the pressure of the sea level?
If you go down to an altitude lower than the sea level, for example, if you go down to Dalol, yes.
Yes, but I think it needs further reading. Maybe we can look into some books and find the change in boiling point of solutions in an atmospheric pressure greater than the sea level.
Oh, an idea came to my mind. Have you ever noticed pressure cooker?
Oh wow, okay.
Yeah, it sells the boiling object, and when it's heated, the pressure increases. It's a pressurized system. Then the water we need boils at a temperature which is greater than 100 degrees centigrade. This is why pressure cooker is more effective than open cooking pots, because it increases the temperature. It raises the temperature more than the opening pots do.
Wow, that's a really good idea. How did you come up with that? Once I remember reading a paper inside a new inside a new pressure cooker, and it shows and it describes well the processes that go inside the pressure cooker, and it shows that an increase in pressure and cooking that rice makes it effective by decreasing the time consumed and the fuel consumption as well.
Okay, so did you hear the bell run?
Yeah.
Okay, so I guess we're done for today. We've completed our experiment, and now we can go and enjoy our break.
Yes.